Good morning, sir. I am Champala Lalani, along with Pawan Srivastava, will present term paper in BER performance of an optical preamplified FSO system under turbulence and pointing error with ASE noise. These are the outlines of our presentation. First, we will understand what is FSO, then objectives, motivation, system description, atmospheric turbulence, pointing error model, combined effect of turbulence and pointing error, characterization of the decision variable, computation of BER, numerical result and discussion and conclusion. First, what is FSO? FSO is free space optical communication that uses light to transfer its signal from one place to another. Here in the transmitter, we use laser or LED to convert the light electrical signal into light signal. Then we use lens to collimate our signal. After that, the signal passes through the atmosphere, and at the receiver we again use collimator to collimate our signal. Now, in the atmosphere there is sunlight, cloud, rain and other atmospheric activities. Due to this, there is a formation of eddies in the atmosphere, and due to this eddies there is a change in reflective index, and this change in reflective index is known as turbulence. And due to this turbulence there is a distortion in the receiver. Now, in spite of this distortion in the receiver, we still use FSO. Why? Because it have high modulation bandwidth, it has unlicensed spectrum, the beam size is very narrow, that makes FSO suitable for secure transmission. FSO are easy to get deploy and redeploy in practice, and low installation and operational cost. Objectives. Here our objective is to evaluate the BER performance of a FSO system assuming non-return to zero on-off keying modulation in the presence of AC noise under weak, moderate to strong and very strong atmospheric turbulence regime and pointing error. Motivation. Actually, using the optical preamplifier boosts the received signal strength very much, and due to this boost in the optical signal we require less power to transmit, and due to this less power it overcomes the I limit restriction on transmitted laser power. Also, it suppresses the limiting effect of the receiver thermal and shot noise and effectively improve receiver sensitivity. And here in our literature survey we have understood that there is no one who have observed the exact BER performance of FSO system under AC noise over different atmospheric turbulence and pointing error. That's why this motivated us to do this work. Now, system description. As we receive our optical signal through the lens, we first collimate the signal. After collimating the signal through the lens, we give the signal to the optical amplifier. Here in this optical amplifier, this boosts our signal. Also, it adds some ASE noise, amplified spontaneous emission noise. Then optical bandpass filter. This optical bandpass filter reduces this ASE noise which are introduced in the signal. After that, we use pin detector. This pin detector converts the optical signal into electrical signal. After the conversion of this optical signal into electrical signal, we amplify this signal. Then we give this signal to the equalizer. This equalizer reduces the distortion that were introduced in the channel. Then threshold based detector to understand the signal is either 0 or 1 at the receiver end. Now, what we have seen in that system description that are only presented here. See, we transmit here NRZ OK data for the transmission of our signal. Then we use preamplifier to boost our signal. Then noise over the time interval t is represented as where phi I is orthonormal function, whereas information signal is represented as this, where xi is information signal in terms of basis function. Now the subsequent signal is integrated over the duration of a bit to get the received signal. This received signal is combination of the information, noise and the atmospheric turbulence. Here H denotes the channel irradiance under atmospheric turbulence and pointing error. After that we give the signal to threshold based detector. Here if the received signal is greater than threshold, then it is decided as 1, and if the received signal is less than threshold, then it is decided as 0. In atmosphere there will be always some amount of turbulence that may be weak or moderate to strong or very strong. Therefore here we will take different turbulence model. First, weak turbulence model. Whenever there is very small amount of turbulence in the atmosphere, then we can use this model. Here to represent the weak turbulence model, we will use log normal distribution and its PDF is given as here. This log normal distribution is little complex, so here we will approximate this by gamma distribution. Then for moderate to strong, we will use gamma gamma distribution and its PDF is given here as. Saturation turbulence is represented by negative exponential statics and its PDF is given here as below. Now when you send a FSO signal to the receiver, there may be some pointing error. It may point away or to the receiver. So this pointing error is represented here as this and its PDF is given here. Now to calculate the combined effect of pointing error and turbulence, we will use this integration. Here if we are calculating for the weak turbulence, then in place of f of HA, function of HA, we will put the PDF of weak turbulence. And similarly, if we are calculating for moderate to strong turbulence, then we will put the PDF for moderate to strong turbulence and calculate the joint distribution. Similarly, we can do the same for very strong turbulence. After putting the value and solving the integration, we will get the values as given here. Now to analyze it more, we convert this in measure G function as given here. Same we can do for the moderate to strong turbulence. For saturation also we can follow the same procedure. Now once we have calculated all these models, then we have to decide either the received signal is 0 or 1. To decide the received signal is 0 or 1, first we have to represent the signal corresponding to 1 and 0. The PDF for the signal corresponding to 1 is represented as here. When no signal is present, then the PDF of the received signal condition on turbulence is expressed as here. Now to calculate the BER, we'll assume that when 1 is transmitted, the received signal is corresponding to 0. Here gamma TH is the threshold value. Now suppose the PDF for sending 1 is here shown. Now we are assuming that gamma TH is the threshold value. If the received signal is below the gamma threshold, that means it is 0, and if the signal received above threshold, that means it is 1. So for probability of error, if we are sending 1, then it should received as 0. Similarly, when we are transmitting 0 and this curve is the PDF for the 0. So when we are transmitting 0, the area under the curve for 1 is above gamma threshold. So this is how we calculate the probability of error. Now probability of sending 0 or 1 is equiprobable. That's why we are representing here by half. Now this integration part we are writing by I1, and similarly this integration part we are writing it by I2. Now to calculate the average BER, we integrate this probability of error over the turbulence again. Now after integrating, Here we again write it in a short form like half PE1 plus half PE2, where PE1 is I1 probability of turbulence plus pointing error, and similarly PE2. So if we want to calculate here, substituting the value from above equation, we get the average BER for weak turbulence as. To analyze the diversity, we need to express the measure G function in terms of hypergeometric function using Slater's theorems. Now at high SNR, the hypergeometric function will tend towards 1 because n not equal to 1 by SNR, that approaches to 0 for very large SNR. So from here we can see that diversity is minimum of zeta square by 2 comma m by 2 under the impact of pointing error, log normal turbulence when ASC noise dominates. For moderate to strong turbulence, we will do the same calculation and convert the measure G function in hypergeometric function and obtain the diversity as minimum of zeta square by 2 comma a comma 2 comma b by 2 under the combined effect of pointing error and turbulence. Similarly, we will do for very strong turbulence, that is saturation turbulence, and get the diversity as minimum of half by zeta square by 2. Now here we will do the comparison of analytical BER performance of the considered FSO system in the presence of ASC noise and weak turbulence condition with pointing error for different value of sigma square. Sigma square is higher, that means fluctuation is more, turbulence is more, so BER will be poorer. Whereas if sigma square is smaller, corresponds to weaker turbulence and the BER will be better. Here we can, that what we can see in the graph. Now this is analytical and asymptotic BER of a FSO system in a normal fading scenario with pointing error and ASC noise for different value of zeta. Here we can see that as we increase the value of zeta, that means the pointing error is decreased, and as pointing error is decreased, the BER is improved and it reaches more towards asymptotic values. That's what we can see from the graph, that it approaches more towards asymptotic value. Here we have taken different value of zeta as 0.65, 1.15 and zeta is equal to 1.45. This is the comparison of the analytical BER of a FSO system dominated by ASC noise in the presence of gamma turbulence with pointing error. So here it is observed that as the value of ABR varied from this to this, the value of sigma square decreases. The value of sigma square decreases, that means the turbulence decreases, and as the turbulence is decreased, the BER performance improves. That's what we can see in the graph. BER of a FSO system in the saturation region for different value of zeta. Here we can see that the pointing error significantly affects the diversity under saturation region. Under strong pointing error of 0.0065, the BER is this and this at 50 and 60 dB. So from here, if we calculate the slope, then that will give us the diversity, and we can see that diversity is here equal to 0.2085, which is nearly equal to zeta square by 2. So, and we can also see that as we increase the value of zeta, that means pointing error is decreasing, and as the pointing error is decreasing, it approaches more towards the asymptotic behavior. Conclusion. So we have studied the performance of a FSO system with an optically pre-amplifier in the presence of ASC noise under the combined influence of turbulence and pointing error. Closed form expression of the analytical BER of a considered FSO system have been evaluated. We have also computed the asymptotic BER expression in the presence of simple elementary function for the FSO system under high SNR region and evaluated the diversity for each of these different turbulent condition. It is also observed that diversity of the considered FSO system is significantly affected by pointing error. The diversity is minimum of this, and this for weak moderate to strong, and very strong turbulence condition respectively. The impact of the presence and absence of optical preamplifier on the BER performance of the considered FSO system is also shown through numerical results. Thank you very much for listening to me patiently.